please.
Good. So good morning. It's always interesting, this Zoom lecture, when you don't know how many people are really following. At least I think we have, how many is it, 40 participants here on the list. One announcement. So I'm Michael Boy. I'm also here. I'm here in Helsinki University at the Institute of Atmospheric and Earth System Research. And I'm leading this group, what you can see on the screen, the multi-scale modeling group, from micro-scale processes to the Earth system, together with Risto Makkonen. Risto was giving yesterday a lecture, I think already, or he gave a lecture yesterday. So we both lead this group here. And as it goes from micro-scale up to the Earth system modeling, and so Risto is taking more, or is more related to the Earth system, and I'm more in the process modeling studies. One thing I want to announce, or I want to remind you again, even I sent an email just for all the people who are in this AGA SSRPs, which we will meet today, first time. We will meet not at 3 p.m. as it is in the program, we will meet at 4 p.m. as we have a group meeting here from 2 to 4, and then at 4 p.m. finish time. So you have 1 hour more break. And then at 4 p.m. we meet in this Zoom room, which I sent you. Okay. But now coming to the lecture. So the lecture, the title of the lecture is Process-Based Modeling for Meteorology, Chemistry, Aerosol System, and Specific Challenges. And this is huge. I mean, Alexander gave just a talk more focusing on the large scales, and I think we could start on his last points. If you remember his last slides on the button where he said the open questions or the problems. And there was also saying that we need more processes in the model to get more understanding of processes. And this is exactly what we are doing. So why we need actually process models and process studies? So the one thing is we need to investigate, as Alexander said already before, we don't understand everything what goes on, not in the chemistry, not in the aerosols. So we cannot solve this only if we have regional and global models. We need really process models where we can put a lot of details inside and then maybe use this knowledge, what we gained out of processes for new parameterizations to put it into the large scale models. We need to test understanding and quality of our process. We need transport phenomena, and we can also do some budget analysis, very simple, with the process models. So, budgeting from different processes, the atmospheric evolution of a species X, and this can be some gas compounds or aerosol, is given by the continuity equation, which means by emission, transport, and things. So this equation usually cannot be solved exactly, need to be constructed by a model. So first you define your problem, what you have, what you want to investigate. Then you make your model. And of course, this already, when you write a model, you need to make assumption because you cannot solve everything. So you create your model, and of course, you have to see how much computer sources I have. Do I have access to a supercomputer? Then you run the model. And this is very important that you have data to evaluate your model. So you evaluate your model, and then normally you realize, it's not working in the way I want to have it. So you improve your model, you do the same. Always the same loop here until you come to a point where you can really say, no, my model is good and I can apply it for science, for atmospheric science. So in the simplest way, you have a box model. You have a box model which you can say it's the whole atmosphere, it's some part of the atmosphere, or it's a very tiny area, but doesn't matter. You have always inside the production, the chemical production. If you now X is your compound or your aerosols, you have the production of this compound. You lost this compound normally by chemical reactions, or when it's particles, you lost them by physical loss, for example, by evaporation. Then you have emission, direct emission of your compound from bioorganic, anthropogenic sources, and we'll talk about the emissions tomorrow. And you have deposition. You lost it just that they stick somewhere on the surface. There, of course, we have to differ between wet and dry deposition. And then you have an inflow. You cannot neglect this, how much comes in of your compound and how much goes out. So you can put the mass balance equation quite easily together. The change of your compound over time is nothing else as the sum of the sources minus the sum of the sinks. And you can put this in one equation. However, spatial distribution of X within the box is not resolved. So normally we say that X is homogeneous mixed in the box. We don't say that. So in the case you have a huge box, then you have to accept that you cannot see any gradients of your compound inside the box. That's the disadvantage. Does it make sense, or when it makes sense to apply really such a box model? One thing is in chamber experiment. It can be difficult to quantify the wall loss. So this is the biggest problem. I mean, otherwise the box model in the chamber is a perfect solution, is a perfect tool to investigate what goes on in the chamber. You can use a detailed chemistry, thousands, 10,000s of equation. You can use a detailed aerosol dynamic because you have no problem with computational resources normally. But the wall loss is the big problem. The wall loss, normally in some cases you get from the chamber, people who run the chamber, you get some rates, loss rates. But what we realized is that normally if you consider chamber experiment in the beginning, they clean the walls. So they make the walls, they put a lot of hours or even days ozone in to get everything out. And they say, now the walls are these. So if you have reactive gases in this chamber, in the beginning, they will go to the walls. But at some times, these walls are also saturated and the stuff comes back. So also if you get these loss rates in the chamber, they are not continue the same over a long time. They change over time. So get the wall loss correct in the chamber is, of course, the tricky point, but otherwise it's the perfect tool to simulate chamber experiments. A little bit easier is with the flow tube experiments. Here, normally in a flow tube, when they have a tube and they put the gases in the beginning in the tube, which react then in the flow, they try to have a laminar flow. So they try that the gases which are interested, which they want to investigate, are not touching the walls, are not having in contact. They have an inert carrier gas around, and in the middle, they have the gases which they want to investigate. And because they try to avoid turbulence, there's only a laminar flow, then it normally works in a way that you really can say the wall losses are negligible. The instruments are very short, the experiments are very short normally, in a couple of seconds, maybe minutes. And so you can use really low time step also for your application, because for your model, it's not very expensive. So I would say this is a way where we also tried a lot of time and where you really can get everything what is happening inside into your model. And you don't have to worry so much about the wall loss. The other way is if you say you use your box model as the whole atmosphere. So a good way of making a very first simple budget calculations for a compound when you know the main sink and the source terms. You can do this. And based on this, you can also calculate the lifetime of a compound. So the lifetime is very important because we need to know how long certain compounds stay in the atmosphere. Especially now when we talk about CO2, which we know everywhere from this climate, COP26 now, has a lifetime of 100 years around. So it stays very long in the atmosphere. But you can calculate the lifetime of other gases which are shorter lifetimes if you know the main sink and source term. So the lifetime is the time a molecule resides in the atmosphere until it is removed by a process. So you have the atmospheric lifetime, tau. It's the mass divided by the outflow. So this was one of your sink term, the loss by chemical reactions and by depositions. But you can also calculate the lifetime only related to the outflow, for example, to the transport. If you take your F out divided by the other source terms. And this gives you then the lifetime, especially for this sink term. Or you can calculate the lifetime by deposition. It's nothing else as the lifetime, the mass divided by the loss term by deposition. So, of course, what I already mentioned, when we talk about deposition, we always have to divide between dry deposition. So when it's really sedimentation and sticking to the surface, also sometimes reactive sticking to the surface, or when it just uptake by cloud, liquid water, and rain out. So, and we can also calculate the chemical lifetime, the lifetime of a compound related to its chemical loss term. So you have the mass of this compound divided by the loss term, by the chemical loss. And there we can have first order loss, or we can have higher order loss. So for example, now in this example, if ozone reacts with NO, we can calculate the lifetime of ozone related to these reactions. And if we take we have the reaction rate from this reaction here, ozone NO, we have an NO concentration. This is a value related to Hüttila, to a rural area, 100 ppt molecules. And if you multiply this together and take, you get 6.5 hours. So ozone will stay about 6.5 hours if you have this lifetime, this concentration of NO. Several chemical reactions inducing a compound. Of course, it's not only the first reaction, but you have also second order reactions and higher order reactions. And all this have to take into account. And this gives us the chance to calculate with a very simple box model. If we know the main chemical loss terms, for example, from a compound, of course, not everything, because there are 10,000s of reactions, but we know the most important loss reactions, we can calculate the lifetime of the compound. For example, carbon monoxide, we know it's about in the atmosphere about a lifetime of about 2 months. Methane, it's the advantage compared to CO2, has a lifetime of, here it's 8 years, let's say 8 to 10 years. And CO2, as I already mentioned, has a lifetime of 100 years. So that's the reason if we now, and methane has still a high contribution to the global warming. So in case we can find some way to reduce the emissions of methane, or also get a higher loss rate of methane reacting mostly with OH, we would have a chance to get rid of methane and then improve the global warming. CO2, it's much difficult. Of course, we have to decrease the emissions. But to attack CO2 in the atmosphere is quite difficult. Methane has a chance as it reacts with OH in the atmosphere. And there you see some other, the terpenes, the monoterpenes, which are very important concerning the aerosol formation in the atmosphere, especially in the rural areas, have a lifetime of hours. So here's alpha-banin, that's the most important monoterpene. It's about 1.6 hours. But there are some who are a little bit even lower, limonene. There's a lower reactor, lower lifetime, and then some there's higher. And the CFCs, which were a big problem in the 80s, when most of you, I think, were not born even, we had a big problem with the ozone hole, because the CFCs, as you see, they have lifetimes of up to 1,000 years. That's the reason they were not attacked or reacting in the troposphere. They came to the stratosphere, and then special chemical reactions started. And then in the spring, in the Arctic spring, they destroyed in the Antarctic spring, they destroyed the ozone there. And we had a lot of ozone depletion in the spring always. But this has been solved. So CFC are banned, I don't know, to 99 or 95% out of the atmosphere. So this was a success story from the scientists and the politicians. And now this is recovering, and we see already the numbers of the CFCs decrease in the stratosphere and not increase anymore. So it's getting better. Of course, they stay also in the stratosphere for a long time, but at least we are not putting stuff up more there. Good. So now you can calculate a chemical species is removed from the atmosphere by chemical reaction with a lifetime of 2 years. So it has a reaction. It's lost by reaction 2 years, and by deposition with a lifetime of 1 year. What is its atmospheric lifetime? So who is fast and can put this in the chat? Or somebody is so fast can say in the chat what it is. So no. Nobody? People still awake? So let's do it easy. So you have the lifetime 1 over tau. It's 1 over 1 year plus 1 over 2 years. So it's 3 over 2 years. So the lifetime of this compound would be 0.67 years. That's the way you can easily calculate the lifetime if you have the different orders. If you know the single ones. So now why is this? So the chemical lifetime gives a measure for the speed of a reaching an equilibrium or steady state of sources in single atmosphere if they are continuous. The compounds with the shortest lifetime reach the equilibrium fastest. And the most important compound in the atmosphere, this is not a lecture about atmospheric chemistry, but I give also lecture in chemistry, and not here in this course, and I say also this is always to the students, this is the police of the atmosphere is OH. And you see OH has a lifetime of a second or even lower. So that's the most important radical in the atmosphere, because without OH, we would have a very polluted atmosphere. OH is cleaning up this. Good. Another application for your box model, if you have a box model, now we talked about the chamber experiment, the flow tube experiment, where it's very good to have a box model. And we talked about making simple first budget calculations, calculate the lifetime of a compound, is when you use your box model and you let it moving with the air mass. So in this case, we can forget about the transport. There's no transport because you stay with the air mass. And you can calculate the change just by taking the emissions, the production, the loss, chemical loss, and the deposition. They are implicit in directives. So there is no outflow and inflow. What you can use this in a way is, for example, and where it is applied also box models, is if you have a very high point source. So for a chimney, a coal power plant, and you know what comes out up. So they have measurements on the top, how much SO2 is coming out, and then you can put your box model in this chimney. So where the air comes out, and you can follow for a couple of seconds, minutes, and calculate what goes on in this very polluted air parcel. If it goes too long, if we go to a further way, you have to take dilution into account. Of course, this air parcel will for a while stay together, but then it will be mixed up with air from the surrounded air. So the temperature will change, the pressure will change, the composition will change. But for the first couple of minutes, you can use it, and then you have to take this dilution factor into account. It's a way, for example, if you have a lot of SO2 coming out of a chimney and you want to see how much sulfuric acid is formed in this first couple of minutes when the air comes out of the chimney. So it's also applied sometimes for big fires, when we have fires and you want to see how much aerosols are formed. So that's another way where you can apply your box model. Okay, in our group we have a lot of long tradition on box model. So I created the first box model. I'm doing this process modeling now since for more than 20 years. And then created the first box model. I think this was already in, what was it, in 2000, the box at this time. And then we had a couple of people like Pontus Roldin, who came from Lund as a postdoc to my group. He had his own box model. And then there came Lukas Bichelstoff from Austria. He had his own box model as a postdoc. And then sometime we were sitting together and saying, why we don't put all our knowledge together, what we have in this, what we gained in the last 15, 20 years, and write a new box model. A new box model, an atmospheric relevant chemistry and aerosol box model. So this was done in the last 3 years, and the outcome was ACA. So ACA is also the model where some of you will work tonight or in the next 2 weeks with. Has the advantage that we made it also with the graphical user interface. So it has a number crunching part, of course, a Fortran code where we have all the science inside, chemistry, the aerosol, the wall loss effect and everything. And we have the graphical user interface. Why we created a graphical user interface is that we said it's a lot of experimentalists, like people running chamber experiments, flow tube experiments, asking us always, could you not do some model simulations for this? And normally we try, of course, we also try to help them or cooperate with them. But it got so many requests that we said we make this model in a way so easy that people can use it from a graphical user interface without knowing Fortran. So you even don't have to know anything in Fortran if you want to run ARCA, because you can do everything from this graphical user interface, which is just clicking boxes, making it ready to run, and you don't have to know anything about Fortran. And we made this code. So this is, let's go to the next slide. This is how it looks like inside you. So all available settings can be come from the GUI. This is written in Python. You can do test runs, you can run the model, you can make parametric input, you can even plot stuff in the GUI. So you don't have to get the data out and plot it. So the GUI provides you also the possibility to plot everything there without opening any file. And inside, of course, in this, then we have the chemistry, the particle formation, the condensation, coagulation, the wall loss, and the, of course, safe data, input data. So we made this code also public available. So this is not only for you tonight, because everybody can work with this code. We make it free available for the community so that we also get feedback. And we got already feedback. The code is open since a couple of months, and we have already, I don't know, 30, 40 people applying the code, downloaded the code. And we improved the code also. Our idea is also to improve the code with the people working with the model. Good, but some of you will meet at 4 o'clock. We'll talk more about that. The next one is a cooler model. So you have your box model, very good working. Let's say you have your box model ARCA here, and you put several box models on top of each other. This is what is the next step. If you say, okay, I'm having my box model, but I want to I'm also interested in the vertical mixing. How much is the vertical mixing? And I can only say that since now more as 20 years, we're working here in Helsinki on this new particle formation. I think you have heard about it, or you get lectures, we had lectures about this banana plots, this new particle formation. And what we found out now in the last years, you cannot solve new particle formation. You really want to model these events only with chemistry and aerosols. You need a meteorology, because there's a special situation that when the boundary layer, on a new day, you have sunshine and the boundary layer evolves, then you have mixing from clean air, from the natural layer, from the stable night layer to the boundary layer, and then the condensation sinks, so the pollution inside the boundary layer decrease, and this enables the particle formation to start in a lot of days. And that's the reason you need to have meteorology, chemistry, and aerosol dynamics if you want to solve a problem, for example, like the new particle formation. And then you need a 1D model. Then you cannot handle this anymore as a box model. Of course, you can use the regional model, for example, from Alexander Mihura, for example, or the WRF-Chem, what Alexander Baklanov showed you today. But they have mostly the limitation that you can only, because of computational resources, at a certain amount of chemistry and at a certain amount of detail in aerosol dynamics. Here in the 1D model, you're not limited. Normally, the computational costs are handled, that you can handle them. They're not so extreme. So you can have a detailed chemistry. Normally, we run our model, which I will show you quite soon, with 10,000s of different equations. You can have a detailed aerosol physics, aerosol dynamics, so we can run with 100 size spins or even higher. You can run with a very short time step, like a second. And the computational costs are still very low compared to a regional model. It is possible, and we have done this also, that you can parallelize the code. So it's quite easy that you can parallelize in a way that you say, okay, the chemistry on this box and the chemistry on this box, they are not interacting at the same time. So you can run the chemistry and the aerosol dynamic on each box on different cores, and then you put the information back to one core and make them vertical mixing. So this is even saving even more time. Time steps can be in the order of seconds, and you can have a quite high temperature resolution. Vertical mixing can be simulated with different approaches, like the K-theories, with different level of difficulties. You can have the 1 point or 1.5. So there's in the literature a lot of different possibilities to take the mixing and to calculate the metrology in this. You can do it two ways. You can read it methodologically, or what we do in our model, you can calculate also the metrology. So we do predict the temperature and the humidity from one time step to the next time step. But in certain cases, which we will talk quite soon, it's also better to read in the metrology, or possible to read in the metrology. But one thing what comes now, the first challenge is when you do such a cooler model is the aerosol dynamics. So when you do aerosol modeling, if you have, I'm not sure how much is the different experience, but if you do aerosol process modeling, aerosol understanding, normally you have a lot of, you distribute the size. Of course, aerosol starts in the size of about 1 nanometer, go up to a couple of micrometers, 10 micrometers, and then you make a size distribution. So, but then in your process, you have to say, how is the aerosol from one size bin going to the next size bin? And there's different methods, and I'm showing you here four methods, which I think the most used ones is you have a fixed grid moving average. So you move when it's condensation, it's moving, your particles are growing. So the grid, this is the grid points, but then inside it's moving because you have condensation. And then you calculate it back to the same grid size. The next way is a fully moving, so it's always moving, and if you have a nucleation, it comes a new pin inside, so it's always moving forward. Then you have fully stationary, that it's always stationary, and just that the bins can go to a next size bins. If there's too many particles here, if they grow too much, then you say a certain part stays in this size bin and the next goes over. And then you have a hybrid fixed grid moving distribution that's similar to the fixed grid moving average, but you have here an area of the size of the particles which are moving. We're not going to in detail because this is an own lecture about particle size distribution, how you do this implementation. But I want to show you this method, for example, which is very interesting, very good for when you want to calculate nucleation correct, because you have new particle formation, you form a new bin, is not possible in a 1D model, as you need to mix them after each time step. And this means that all the boxes, the aerosol size distribution, each box needs to have the same size distribution. They cannot change. And in this fully moving, the size bins will be different after each time step. So you cannot mix them with the box around. So this is already what limits a little bit your selection, what kind of size distribution, a representation for the aerosol size distribution you want to apply when you have a 1D model. But still, you see, you are still left, you still can use this three, but this one is not anymore possible if you talk about a 1D model. Then what is a very challenge is the upper and lower boundaries in the 1D model. So the meteorological model solves the prognostic equation for the meteorological variables. The prognostic variables at the upper boundary of the model domain should be constrained with available data. So what we are doing, because we have this large-scale weather phenomenon, and what we are doing to handle this in the 1D model, our 1D model goes up to 3 kilometers. We read in the ECMWF data at 3 kilometers. So the geostrophic wind at 3 kilometers, the temperature and the pressure at 3 kilometers, and give this as fixed values in the model. Otherwise, we calculate the temperature, but we get in these values from the ECMWF. Then you have to take special care on the upper boundary condition for gases and aerosols. They have to be set in a way that you have an outflow, otherwise you accumulate stuff inside the boundary layer. But Of course, if you set everything to 0 up here and then you have a strong outflow, then you overestimate the outflow. So this needs to be handled with care. Special risky part is this with ozone, for example, if you have a 1D model up to 3 kilometer. One option is to take the CAMS data, for example, or some other data and put them in as 3 kilometer. So you have, because as we know, ozone has higher concentration, we have a downflow of ozone from the stratosphere, troposphere, and you need to have here the ozone concentration fixed based on some measurements. Otherwise, your ozone concentration in the 1D model will never get correct. In the lower part, deposition, of course, there are different methods to calculate the deposition correct. We have now in our model a very detailed deposition module, which is based on a code by Lawrence Ganzefeld, who is professor in the Netherlands. But there are different ways. You can also use simplified, but deposition needs to be solved. And now we talk about dry deposition in the canopy, in the urban and in the rural canopy. So when we can apply such a model, so 1D model, and one thing is you have to take into account the 1D model is not taking like a regional model, the air mass if the air mass is changed. So one very important or one easy location is, for example, the smear station. I think you had or you will have lectures about the smear station, our station Hyttila, and this is actually a picture from Hyttila, from this, I don't know which direction, and it's a homogeneous landscape in each direction. So you see you have pine forest in 50 kilometer, 100 kilometer in each direction. And you can say, you can make the assumption what comes into your model from this side goes out of this side. So there's everywhere the same emissions coming, and there is no anthropogenic high emission source. So you can say that you still have to take care on the anthropogenic important gases like SO2, NOx. This CO you have to read in. They have lifetimes of longer than a couple of hours. So CO 2 weeks, SO2 CO 2 months, SO2 2 weeks. So you have to consider them. But otherwise, you can put your box model here, and you can even, what we are doing, nudge your lowest boxes with the value measured at Hyttila. Nudging means you push the model in the direction of the measurements, but you don't take the measurements. And then you can get quite nice results. And I want to show you one thing now here. So this is now our model SOSA. So it has an emission, the Megan code, we calculate the emission also from the forest. We have the aerosol dynamic. This is not anymore. This is now new version. Then we have SCADIS, which is responsible for predicting the meteorological data and the mixing, the chemistry and the deposition. And one example, what I want to show you now, what we have done with this model is, for example, there was always assumed that SO2 reacts with OH and forms sulfuric acid. So this was already the idea, but we also realized that we underestimate SO2 with this kind of approach. So we thought either the sink or the source term must be wrong. So then, but we were not sure. We believe that our sink term is calculated okay, because we know the aerosol, we have measured the aerosols in Hyttila, but we saw the source. And then there was Thorsten Berndt, who is a scientist at Leipzig, at Tropos in Germany. He did some experiment where he realized when he put, so this is now, for example, here, let's take limonene, so, or alpha-binding here in the chamber, and alpha-binding, and here he puts an OH scavenger inside. So when scavenger means that he got chemical, a loss term for OH, so all the OH were gone. There should be no more sulfuric acid in the chamber if you have no OH, if you believe that sulfuric acid is formed over this reaction. But what they saw, that they saw also quite a lot of sulfuric acid. And even with high concentration of reactive terpenes, they see that it's nearly the same with OH and without OH. Not the same, but it comes quite close. And for limonene, it was even the same. So this was the question, what happens there? And make the story short, after it's not like this, that it took only a couple of minutes. After long work, they found out that these reactions, the Greek stable Greek intermediates, which are formed, and this is already some reaction which is in the master chemical mechanism, is this Greek can react with SO2 and form SO3, and SO3 that can form sulfuric acid. And this blue reaction rate was in the chamber, was in this master chemical reactions, or was the one which was accepted. But they found out that it's about 10 times faster, these reactions, for all, for alpha binding, beta binding, and limon. It's about 10 times faster, and also for isoprene. So we put this then in the model. In our model, first we checked it compared to the measurements, Hütila and Hohenpeißenberg in Germany. It's a station close to Munich, where they have long-time OH measurements, and we see that we can improve our sulfuric acid modeled compared to the measurement dramatically if we take this into account. Then we used the 1D model and tested how important this is in the atmosphere, really. So we used our SOSA model, put this in, and you see the color code tells you now the amount of sulfuric acid produced by OH divided by the amount of sulfuric acid produced by OH plus the stable gradient in the medium. So if it's red, then it's only coming dark red, and it's only coming from OH. But if it's more bluish, then you can say there's also a high contribution, and up to what we see here, up to 30%, especially in the nights time when there's no OH or less OH available. This term is quite significant. And we see in the first 50 meters, it can have over the average, over the day, a contribution to 20–30%, and that's a lot. But then if you go higher up, you can say, okay, then it is not anymore so important, so crucial to the sulfuric acid, to form sulfuric acid. However, why it is still important to have this also in the regional models, in the global models, included this reaction, is because also the regional model and the global model, they try to evaluate the sulfuric acid concentration because it's important for the particle formation. So they take the measurements at the ground, and the ground measurements are normally here. They're not up in a couple of 100 meters. Here are the stations, here they measure in this. And if you take the sulfuric acid measurements measured, and your model, and you tune your model in a way that it fits the concentrations without having this in, then you will overestimate your sulfuric acid here. So it's also important what we showed, that you have to take this into account if you want to get it correct. But there's still a lot of uncertainties in this Krigis forming sulfuric acid, which we will not go because we have a lecture now on chemistry. Then another way what you can use your 1D model, and this is what we are doing now very intensive in our group, is to use the 1D model along a trajectory. So you have a calculated trajectory, and then you come to a point, and there you, along the trajectory, you get the chemistry and the aerosol. It's the same what I showed you with the box model, but now you use the 1D model. So first you calculate the directories, and we're using FlexPart here in the group. You calculate for each hour directory, and this is Hütila. So when they arrive in Hütila all, and you see at this special day, they all came from the northeastern part, northern western part, from the, what is this, Greenland? No, there is Greenland. So quite far away they came to Hütila. Then you calculate the emissions along these directories. And this is now the emission possibility at one time. So this is just at this one point, one single point. You get this kind of possible weather emission. So the residence, so it's a little bit of probability where the emission could come from 7 days ago. This is provided by FlexPart. And next what you do, you calculate then for each compound along the main trajectory the emission as input to the model. And then you can apply SOSA and run it. But this is now for alpha-bindene, and you see there is very no emission of alpha-bindene over the ocean, but then you get something here. And then when you come here, we have high emission of alpha-bindene, and it comes to Hütila. But remember, this is not from the trajectory, this is from all these areas. So it's not easy to run. If you want to do detailed studies, it's not so easy if you get the emission in your model correct, but you have to put a lot of effort that this is correct. Otherwise, your outcome will be not make no sense. So we tried this, for example, in the paper we published 2 years ago. First, where we calculate, first this paper also showed a new mechanism for the peroxy radical out-oxidation mechanism. If you are interested, I'm not sure if there's chemical lectures in this course here, but if there's a chemical lecture, they will also talk about this highly oxidized molecules and rewrote the chemistry code for this. And if you apply this model, then along the directories, the same way I showed you, just you can see this is now the measured and this is the modeled particle formation. So this nice banana plots, what we see normally here. And we see that the model is doing a quite nice job concerning getting the particle formation correct. We are applying this kind of model system now for different kind of areas, like for urban areas also. In my opinion, this we talk about, and I think you have also lectures here about urban air pollution. We have this urban air pollution with strong mixture of chemistry and aerosols, which we are not able to put in the regional model. I think the regional model is doing a fantastic job. But if you really want to go understand what goes on, and you have 10,000 reactions, and you have huge amount of aerosols and composition of aerosols, and you want to know in details understanding, then this kind of approach, what we are doing here is have the possibility along the directory that you also know where's the source is coming from. You can shut down different sources and you can see what is really causing the aerosol, the air pollution at certain points, at certain places. Good. What to remember from these lectures? Box models or zero-dimension models are good tools to simulate chamber and flow tube experiments. However, wall loss effects can be difficult and special knowledge about the experimental setup is required to get it correct into the model. Applications of box models with the airflow for high emission point sources are useful for short time scales. Otherwise, you have to get to this dilution effect into account. But if you want to stay very short, couple of minutes to see what happens in the next couple of seconds or minutes, then you can also put your box model direct with the emissions from the source. Because if you say your box model is only 1 centimeter, 1 cubic centimeter, and you have this big chimney, can you assume that your box stays in the mainstream for a while, but not for too long. Single box model can be used to make budgets or describe the situation in a well-mixed atmosphere. For special gases with long lifetime, this is definitely easy. But also for other gases, you can apply a box model to make a first simple budget calculations. How long is the lifetime? How long this will stay if you know the main sink and source terms. 1D models like SOSA can be applied locally in homogeneous landscape with less anthropogenic impact. You should not put SOSA, for example, in a town like Moscow or Beijing, because there you have so much different air masses mixing that it makes no sense to have it there. But in a place like Hütila, where we have the homogeneous landscape around, there you can say, okay, we can apply SOSA. The best way for me is to apply a Lagrangian model like SOSA FlexPod system follow the air for backward trajectories or further development of an air mass. So this is something what we are doing active here in the group for different rural and or urban stations to investigate the atmospheric, the chemistry and aerosol physics at certain places, starting 7 days backward and coming to the location. Good. I think that's all what I want to say.